So if you can remember, okay, loading happens at the evaporator. So this is a tube. Unloading happens at the condenser, that is the process, condensation process. And there is a tube. So loading happens when flow of refrigerant or transport, okay, passing through a tube. We call it evaporator because here the transport is in saturated form, okay. Condensation also mostly saturated form vapor turns to liquid and energy or the heat release, unloading taken place. Dispatching is here. So this is what this doing is taking this evaporator, the energized or the loaded transport received from the compressor or the dispatcher by means of suction, and then pump that transport or dispatch into the unloading side, okay. And here the metering device or the component, the other component responsible for the transport ready, give me a second, Dr. Zaina. Sorry, Vitala. So this is the situation. So loading taken place, okay, loading taken place, low temperature, and unloading taken place at high temperature, okay. So QL and QH, and you have W here, the work done, okay, work done on the transport, okay, transport, work done on the transport. So you can see this component, we called it compressor here, that's all right, but this component is for the purpose to do this dispatching of transport. So the component to operate it needs energy. So that is we call W, and this is the metering device. This metering device, yeah, this metering device. You can call this a capillary or expansion device. Okay, so we consider R600E for this case. R600E. So we have learned this very well. We have learned this very well because to came to this slide, we came to know about the pressures and all. We came to know about the pressure. See, low pressure, R600E 2.219 at the low pressure side. High pressure side at 45 degrees, it is 6 bar. Okay, the pressure difference. Two components responsible. One is the dispatching and the return release, the other one. In standard terms of the components, this is the compressor and the metering device for expansion. Okay, yeah. So that is very important. So let me take, if I need to continue this in the same slide, also possible, but let me take this part.
Excuse me, sir. Sir, we can't hear, sir.
Yeah. So now, okay. Yeah. So this is the left side of this system. Okay, this left side. Okay, left side here. So I'm trying to let you understand this very well. The same thing, two different pictures, one with the graph pressure, and the other side it's energy axis. We call this enthalpy. So for loading and unloading, yeah. So here the return ready component and the refrigerant or the transport, this is the direction it is flowing. Okay, this is the direction it is flowing. And here you can see the direction. Okay, you can see the direction. So you can see the direction here. Follow the cursor I'm pointing. This is the direction I'm pointing. So how to make high temperature, high pressure to low temperature, low pressure. Okay, that's the point. Okay, so high pressure, transport, turning into low pressure. Okay, that is one thing. And here, the high pressure, the saturation, and you can see high temperature as well. Okay, high pressure, high temperature. High temperature. Transport turning into low pressure, low temperature as well. So if you can understand this very well, you have to think a bit. If you can understand this, you are done. Okay. The strategies here, the technology you are using in this vapor situations, the technology behind this, what we call flashing, is the technique. The technique applied creating a flash. Okay, creating a flash. This is the technique or the technology. Technology is creating the flash, creating a flash. Okay, so this is the technique or the technology, creating a flash. Okay, and you know what flashing for? Flashing effect. Okay, so creating a flash means now you know that in flashing, liquid, initially liquid, okay, initially liquid, initially in liquid form, okay, in liquid form, subjected to, okay, sudden lowering of temperature, okay, forming, okay, forming low pressure, low temperature, liquid and gas mixture, okay, forming low pressure, low temperature, liquid and gas mixture. So if I take this example, so this you can see. So let me take part of this because I asked you to go through this, the video related that explained everything very well. This is the situation. Okay, this is the situation. Yeah, like this. Inflation. Okay, so this is the situation. This is the, okay, sudden lowering of temperature, forming low pressure, low temperature liquid and gas. So this is the one. So this gas means energized, and the energy received from the liquid itself. As a result, both gas and liquid becomes cold, and this is in saturated conditions. Okay, both are existing together in the same space. So this is saturated condition. Okay, so this is the strategy. Okay, this is the strategy. And for this strategy, there are two components functioning. Okay, so let me go for a new slide. Let me go for a new slide. If I take this, you can see in this example, not that. The complete one, this one. Two components. One is the dispatching. So what this is doing is, receive, okay, or evacuate or suck the energized vapor, okay, because when the loading taken place, yeah, suck the energized vapor, low pressure, low temperature, and then discharge it for the high pressure, high temperature side as high pressure, high temperature gas for unloading. Okay. And this metering device or the flow control, let's say you have one is something like a pumping device. So this pumps and this controls. What happens is one side become something like sucking the liquid, and one side becomes sucking the fluid or the vapor mainly, and the other side become pressurized because of this flow metering. Metering means control. Okay, flow metering. So there is a limitation for the flow. Okay, flow metering. Yeah, so you cannot let heavier flow as what the compressor or the dispatcher expected. So there is a control. Okay, there is a control. So if I take the two components, this, and the other component, this. Let me take big. other component. You imagine, okay, you imagine this is trying to receive fast, okay, this is trying to receive transport at a higher rate, okay, this component, but this component at this end trying to control, okay, trying to control the transport as trying to control this transport so that the compressor or the dispatcher will not receive as expected, so that dispatcher is not receiving as expected, okay. So this is the situation, is not receiving transport as expected. So the dispatcher is trying to receive, but the control, the metering device is really restricting it, okay, trying to control or restrict, okay, or restrict, or even limit. This is the situation. So this one is trying to receive, but this is trying to limit. As a result, there comes a balance. So trying to receive, and also this has a capacity to trying to dispatch. The received transport at a higher rate, okay, trying to dispatch the received transport at a higher rate. But this component is trying to control or limit the transport, okay, so that the dispatcher is not dispatching the received transport as expected, okay, as expected, is not dispatching received transport as expected, means so that the dispatcher is not dispatching the received transport, or dispatcher faces challenges, okay, face challenge, to dispatch. Okay, to dispatch the received transport as expected. So this is the situation. So I will take this 4 situations. Okay, I will take this 4 situations. Yeah. Okay, this is the 4 situation. So what happens is, as a result, these 2 components, of course, somehow must strike a flow balance. Okay, so need to strike a flow balance. Okay, so that's how. So as a result, both the components strike a flow balance with lower pressure at the receiving end of the dispatcher and a higher pressure at the delivering end of the dispatcher. Okay, so this is the outcome of that. As a result, yeah. So one side is low pressure, the other side is high pressure. The 2 components responsible, of course, dispatcher is there, but the control device or the metering device makes this high and low pressures together with this dispatcher. Okay, so these are the 2 components responsible for these 2 pressures. Okay, high pressure and low pressure. Okay, high pressure and low pressure. So here, okay, this will be in liquid form. Okay, liquid form at the metering device inlet. Okay, liquid form. Okay, yeah. So please follow very well. Then here taken place the flash. Over the here taken place the flash. Okay, because of this metering. Okay, throughout this, the flash is taken place. Okay, flash. So let's say end here. Okay, flashed liquid. Okay, this is flashed. So here becomes low pressure, low temperature. This striking of the balance This side become high pressure, high temperature, SI. Okay, low pressure, low temperature, and high pressure, high temperature. So one is the flash effect, the other is the dispatch effect. Okay, one is the metering effect, the other is the dispatch effect. So one is the flashing effect, the other is dispatch. Means you have to suction this suction, and then here high pressure means you have to compress this. Compression brings the transport from low to high pressure. So suction and compression. Of course, for the compression, delivery of compressed transport, you have to have a suction as well. So suction and compression. So that's why we call one component is compression, vapor compression, and the other is this metering device. I believe we have some little understanding about this, provided that you have gone through that flashing, understanding flashing video. Okay, so that's why. So finally you can see, because of this, you have this. Okay, you have this, all the components connected with the two responsible for the high and low pressures. Okay, compressor and the metering device or the capillary. And you can see these two components. Responsible for high pressure and low pressure sides. Okay, so I have explained this in different ways now. Okay, high pressure and low pressure sides responsible. Okay, so that's all about this. I believe you can understand how strategically, or what's the technology, or what's the arrangement of this strategy to make this loading and unloading happen. So if you go through the videos, you can understand this to the fullest. Yeah. So today, with this one, now I'm going to look into this. Okay. So let me take a snapshot of this. Oh, I will go for R600D, not this one. Okay, R600D, because the example is R600D. R600D. Okay, this is R600D, you can see. That's why the school pack is very useful. This is the liquid vapor dome here. So see, slowly narrowing, okay, the width of this, and finally it's done here. Okay, it's a completion, the critical point. From the critical point towards right, this represents the vapor or the gas portion. And from the critical point towards the left is the liquid presentation. So in between, proportionately, you can see the liquid vapor mixture. So that's why we call this liquid vapor dome. And at the critical point, it is, we would say it is in gas form. Well, yeah, above critical point, of course, yes. That's it. So here, so as I mentioned, let me take a snapshot. Pressure enthalpy. You can see here pressure and enthalpy. Pressure and enthalpy. This also last week construction, this is pressure. This is enthalpy H. So here also you can see P and H here. Okay, P and H. And then here you can see for the loading there is a corresponding pressure. Okay, and for unloading there is a corresponding pressure as well, as you see here in the previous learnings. Okay, so let me take body. I'm just putting here, I'm not checking any scale or any specific values. Unloading. So high pressure and low pressure. Same way here, 2 bar and 6 bar. So high pressure line, low pressure line. It's the same. Okay. And for flashing, I have mentioned to you that entering into the metering device should be in liquid form. So this is the liquid line presenting. So liquid form means it should be on this liquid line of the vapor dome or little inwards. Okay, quite interesting. Okay, and I'm drawing the other one. Metering device, no change of energy. So this should come like this. Okay, so this point should come here. Okay, so 0.3 and 0.4. Something like this. Okay. In a very effective loading, okay, once the transport is fully loaded means this point 1, okay, this point 1 will be no more liquid, okay, will be no more liquid, and the minimum is here on this vapor line of the vapor dome, vapor point of the vapor dome, but there can be little more, okay, towards the gas phase. Okay, little more towards the gas phase, and let me explain what that means. Okay, And now you can see as 1 and 2, here also there is a enthalpy increase when compression works. Enthalpy increase. Okay, I just put that. Okay, enthalpy increase. Okay, because of this. So you can see this point 2 is outside the liquid, sorry, gas dome. Outside this gas line, okay, of the or the vapor line component of this dome. Okay, so that's how these points. No, I take that out. 1, 2, 3, and 4 taken place. Okay, means there are corresponding processes. Okay, there are corresponding processes. I hope you can understand this. Flow directions, you can see as usual. You have seen the arrows. So you have seen the arrow lines, you can see it. Pressure line here. So how to okay, this is the high pressure line, continuous, but I put it in 2 colors. Okay, this is the low pressure line. So loading taken place, unloading taken place, then dispatching and the metering or return ready. Yet I will make this big, this component. Okay. Always connected with practicals. Like this. Okay. That's why you can see that in evaluation of this kind of cycles, pressure is one of the key parameters because this loading and unloading, the energy releasing and energy receiving taken place at saturated liquid vapor conditions. So there are definite or the specific pressure levels, low pressure and high pressure. So you have the pressure lines. And here the other direction should be you because you are involved with energy balances. So the other is energy line. And corresponding to this open nature of systems, of the components, there are 4 major components. So that energy line is the enthalpy line. So this pH diagram is one of the very important diagrams in analyzing or looking into the systems. Okay, pH diagrams. It's very important. So let me take this. Okay. I just draw this. Yeah. See, it is something like this. Okay, it is something like this. So, pH diagram. Diagram for cooling systems, so vapor compression, refrigeration systems. So you know how this appears now. There are reasons to have this. So you should know this. Okay, you should know this. Yeah, how this story unfold up to this level. So you should understand this. It is very important. That's why I explain everything from the beginning as a policy, step by step, known to unknown. Okay, yeah. Simple, starting simple and then step by step, it is always known, always simple. So that's the approach. So you came up to this level. Okay, and now I'm going to introduce you two key terms we are using in these technologies. You may have not physically seen a cooling system, but you should be able to, what? You should be able to imagine this. Okay, you should be able to imagine this. Yeah. So slowly, practical, we are reaching a bit more analysis level. Okay, mark it here, and then I will draw another line. I put a direction here, end point, like this. Oh, sorry. So this should be, yes. Okay, very nice. And I will mark one more. Then you can put your own notes if you need. Here. Okay. You can see. Line color. Sorry, not very good. No, that is quite good. Okay. Here also I put the same line color. It is quite eye-catching color. Okay. This one also. thought quite interesting this. There's some. Okay, good. Okay, and I'm going to mark some important points. One point. Give me a second. Point one. Notice a point one. One point. Another point. Okay. Yes. How many points this has? 7 points. 1, 2, 3, 4, 5, 6, 7. 7 points. Okay. This is 7 points. So here I will add some names. Additional points. I put 1 dash. 1 dash. Because this is belongs to something has a connection with the 1. This one I put 2. Okay. This is 3 dash. Okay. Now one more point I had to put. No choice. Okay. One more point I had to put. Yeah. Let me take a new slide, duplicate of this. To try to understand this very well. 4 dash. Okay. And let me put this one. Yeah. Okay. Even though I mark 4 dash here, there is no point. Okay, no red circle. Now you should know that. No red circle. Yeah. So you have 7 points. Okay. So yes. Okay, so we are going to learn this. Okay, you're going to learn this. Okay, you are going to learn this. Here, 1, 2, 3, 4. Okay, 1, 2, 3, 4. If you take the points 1, 2, 3, 4, let me try my best to squeeze all here. So here you're flashing knowledge, understanding transport, all very important. 3, 4. So this 1, 2, 3, 4 components, as you see, points, as you see. Conditions. Conditions means pH conditions. So entering and leaving. Okay. Leaving for major components. You can see that for the compressor 1 to 2. Dispatching. Okay. So instead of components, let me say processes. Connected in the cycle. Not in the cycle, I just put in this cycle, refrigeration cycle. So that is obvious, okay? That is obvious for you. So how about the other points? Okay, how about the other points? So no matter the diagram is here or not, okay, no matter the diagrams here or not, the points are there, okay? Okay. Yeah. So let me take the point 3 dash now. So you know that 3 to 4 flashing is taken place. Okay. So 3 dash is the limiting point. Is the limiting point of 3. Okay. Limiting point of 3 entering the metering device. Okay. 3 dash. So what is 4 dash? Corresponding point 4. Four 3 dash is 4 dash. It's very interesting, this explanation. So I'm putting all the reasons. Okay. Same way. If you need 1 dash, 1 dash is not the limiting point, but this is the ideal point. Because once evaporated all, yeah, ideal point of 1 is all evaporated, just nice, okay? All transport turned into saturated, that's a pointer, saturated vapor. X is 1. Okay, X is 1. Okay, 1. But this is the issue, which is difficult, which is difficult to assure as 1 dash. Okay, assure as 1. Okay, which means ideal point of 1, the transport turned into saturated vapor, which is difficult to assure as 1, means 1 brings to 1 dash. Good, but it is very difficult, which is instead of which difficult, let's say which is ideal point, which is the ideal of 1. Ideal of 1, that is okay. Which is the ideal of 1. Okay, which is the ideal of 1. Very nice. Okay, ideal of 1. Here there is one point I didn't draw. Okay, even now I am not drawing that, but I will just show you only. If 1 dash happens to be 1, you have another point in between 2 and 2 dash. Not the 2, neither 2 nor 2 dash, but in between. Okay, in between. And also there are some complexities if I add this here. There are some complexities if I add this here, so let me not draw this at this time. Okay, if I need to draw 1 at 1, 1 at 1 dash, then corresponding 1 dash to 2 line I will draw after. So how many points here now? 1, 2, 3, 4, 5, 6, 7. I believe you have some understanding about this. Okay, I believe you have some understanding about this. There's a frame here. Should be okay. I have to share with you what delta T LSC, what delta T DSH, what delta T SSH, and also I have to mention you the liquid cell in this cooling system technologies, the liquid cell. Remind me if I forgot to explain this. Okay. Are you okay with this master slide? Are you okay? I hope you all can hear. So let me start from the beginning. So here, pH. Oh, a pH diagram R600A. Okay, so this is the one. So there is a draw cycle. Okay, see what happens here. It's asking evaporating temperature. It's asking superheat. It's asking for pressure drops. dP means pressure drops. Condensing temperature, subcooling, pressure drops, condense and liquid lines. Okay. So let me take this and also let me take this as well. Okay. How to get this? Here in this, okay, you can see our first case, discharging or unloading at 45 degrees Celsius, loading at 10 degrees Celsius. So for this one, unloading condenser 45 degrees Celsius, loading means at the evaporator 10 degrees Celsius. Okay, and now evaporate, you have the superheat. What superheat means? Okay, here 1 dash and 1, okay, between 1 dash and 1 there is a temperature rise, that is delta T. I put here suction superheat. Okay, this is we call suction superheat. Superheat delta TSH. Okay, so let's say this is a 5-degree rise. So 5-degree delta T. So you can have the Kelvin scale rise. So Celsius both are okay, because it's delta T, only a difference. Yeah. So subcooling, again, subcooling. What is this subcooling? So I will go to this. Delta TLS means you have to make sure at least this 3 dash is the limiting point. Okay, 3 dash is the limiting point. 3 dash is the limiting point. So I will use this one maybe. The final slide is this. So delta T subcooling, this is superheat suction. So delta T subcooling is this one. So this is we call the liquid subcooling. Okay. Okay, subcooling. Because subcooling means it's related to liquid. Superheating means it's related to gas. Okay. So liquid subcooling or just simply subcooling. So because after unloading turns into liquid, it is very essential for flashing. If no liquid, no flashing. Okay, so there should be a complete liquid form for the flashing effect here. Okay, because if there are vapor, we have difficulty in bringing these sudden pressure drops. Okay, so we have to assure liquid subcooling. Later I will explain you the liquid seal. So liquid subcooling. Let's say we have another 5 degrees subcooling. 5 degrees too much, but let's say 5 degrees subcooling. I will put subcooling 5 degrees. See what happens. So cycle name R600A. Understanding transport in refrigeration. Okay, yeah. So that's all. And the pressure drops means, okay, pressure drops means, let me explain to you. Sometimes if this piping are not in proper match with the transport rate, there can be pressure drops. In a very good design, no pressure drops.